40 feet below the surface of the Coral Sea, something is about to break the laws of physics. In less than 3 milliseconds, faster than you can blink, a strike accelerates to 50 miles per hour. The water around it literally boils. The impact creates light. Not reflected light, generated light. The creature responsible is smaller than your forearm. This is the mantis shrimp, and what it can do should be impossible for something made of flesh and bone. Today, we're going to break down the biological engineering of the most violent predator in the ocean, pound for pound. What you're about to learn will change how you think about the limits of evolution. The encounter. Most divers in the Indo-Pacific never see them. Mantis shrimp spend their lives in burrows carved into coral rock, watching the world through compound eyes that can rotate independently. They look almost comical, like a praying mantis crossed with a lobster, painted in electric greens, blues, and reds that seem too bright to be real. But marine biologists know better than to get close. In the 1960s, researcher Roy Caldwell was studying these creatures in his lab at the University of California, Berkeley, when one of them, only 6 inches long, struck the glass wall of its aquarium. The quarter-inch thick glass shattered instantly. Caldwell watched as the shrimp calmly walked through the broken wall and disappeared into a drain. He found it 3 rooms away. This wasn't aggression. The shrimp wasn't trying to escape. It was simply doing what mantis shrimp do thousands of times throughout their lives. It was hunting. And the weapon it uses, hidden in plain sight at the end of its arms, has fascinated physicists, engineers, and military researchers for decades. Since that incident, aquariums around the world have learned to house mantis shrimp in acrylic tanks specifically designed to withstand their strikes. There are documented cases of mantis shrimp breaking through double-layered acrylic, cracking PVC pipes, and even injuring handlers through thick rubber gloves. But here's what makes this even more remarkable. The mantis shrimp isn't some rare exotic outlier. There are over 450 known species, and they exist in oceans all over the world. Some live in shallow tide pools where children play. Others inhabit depths of over 1,500 feet. And every single one of them is armed with a weapon system that defies what we think biology should be capable of. The anatomy of violence. How does a 4-ounce creature generate a punch that can crack crab shells, split clams, and shatter aquarium glass? The answer is hidden in its raptorial appendages, the 2 club-like structures it keeps folded beneath its head. To understand what makes them special, you need to see them at the microscopic level. The clubs themselves are made of hydroxyapatite, the same mineral in human bones and teeth. But the mantis shrimp doesn't just use this material, it engineers it. Under a microscope, the club reveals a structure that looks like something designed by aerospace engineers. There's an impact region made of crystalline hydroxyapatite, arranged in a herringbone pattern, the same pattern used in carbon fiber to resist fractures. Beneath that is a periodic region where the crystals are rotated in helicoidal layers, creating a spring-like structure that absorbs shock. In other words, the mantis shrimp's fist is built like a composite material you'd find on a Formula One race car. Materials scientists at the University of California, Riverside have found that the impact surface has a hardness comparable to industrial ceramics, while the underlying layers provide flexibility that prevents catastrophic failure. But the club is just the projectile. The real engineering is in the spring mechanism that launches it. Inside the mantis shrimp's arm is a saddle-shaped structure made of compressed chitin and protein. Before a strike, specialized muscles pull this saddle backward, storing elastic energy like a compressed bow. A latch mechanism holds everything in place, building tension. The muscles themselves aren't particularly powerful. They don't need to be. They only need to load the spring. And then, in an instant too fast for most cameras to capture, the latch releases. The saddle unfolds like a spring-loaded mousetrap, catapulting the club forward at an acceleration of over 10,000 Gs. For context, a bullet leaving a gun experiences about 30,000 Gs. A professional boxer's punch? Around 50 Gs. The mantis shrimp is generating forces closer to artillery than biology. To put this in perspective, if a human could accelerate their arm at the same rate, accounting for size differences, you could throw a baseball into orbit. The kinetic energy generated by a 4-inch mantis shrimp strike is comparable to a .22 caliber bullet. The entire strike, from the moment the latch releases to the moment of impact, takes between 2.7 and 3 milliseconds. A human eye blink takes 100 to 150 milliseconds. By the time you could even begin to register that the mantis shrimp has moved, the strike is over, and the mantis shrimp has already retracted its weapon back into the cocked position. But here's where it gets truly strange. The impossible consequence. When the club moves through water at 50 miles per hour, it creates something that shouldn't exist in nature: cavitation bubbles. Water, despite being a liquid, has limits. When an object moves through it fast enough, it creates a zone of such low pressure that the water itself vaporizes, turns into gas for a fraction of a second. These are cavitation bubbles, and when they collapse, when the water rushes back in to fill the void, they release energy. A lot of energy. The collapsing bubbles generate temperatures of over 4,000 degrees Celsius, nearly as hot as the surface of the sun. They create shock waves that propagate through the water. And in that brief moment of collapse, they produce light. Actual photons. This phenomenon is called sonoluminescence, and it's the same process studied in advanced physics labs using specialized equipment. The mantis shrimp does this every time it hunts. So when a mantis shrimp strikes, its prey is hit twice. First by the club itself, traveling at 50 miles per hour. Then, a fraction of a second later, by the collapsing cavitation bubble. It's a 1-2 punch at the molecular level. Because here's the final twist. The mantis shrimp's club should shatter after a single strike. But it doesn't. Others in the gallery of impossible biology. The mantis shrimp isn't alone in possessing abilities that seem to break the rules of biology. Consider the pistol shrimp, a close relative that has evolved a different but equally absurd weapon. The pistol shrimp has one oversized claw that it can snap shut at incredible speed. The snap creates a cavitation bubble that generates a sound wave reaching 210 decibels. For reference, a gunshot is about 140 decibels. A jet engine at takeoff is 150 decibels. The cavitation bubble reaches temperatures of 4,700 degrees Celsius, hotter than the surface of the sun. During World War II, submarines would hide near reefs populated by pistol shrimp because their constant snapping created a wall of noise that made acoustic detection impossible. Then there's the bombardier beetle, which sprays a boiling chemical mixture from its abdomen when threatened. The beetle stores hydrogen peroxide and hydroquinone in separate chambers. When threatened, it combines them with enzymes in a reaction chamber, creating a mixture that reaches 100 degrees Celsius and is expelled with an audible pop. The beetle is essentially carrying a chemical weapon system in its body without blowing itself up. The cone snail, a slow-moving marine mollusk, hunts fast fish by carrying up to 200 different venom compounds. When it stings a fish with its harpoon-like tooth, it delivers a cocktail that shuts down the fish's nervous system in under 2 seconds. Some cone snail venoms are so potent that a single drop could kill 20 humans. The tardigrade, an 8-legged microanimal, might be the most indestructible organism on Earth. Tardigrades can survive temperatures from near absolute zero to 300 degrees Fahrenheit. They can withstand pressure 6 times greater than the deepest ocean trenches. They've been exposed to the vacuum of space, and when rehydrated, they simply woke up. Scientists have revived tardigrades that were frozen for 30 years. The electric eel generates up to 860 volts of electricity. But here's the remarkable part. The eel can remotely control its prey. When it detects a fish hiding in mud, it emits high-frequency pulses that cause involuntary muscle contractions in the hidden prey, making it twitch and reveal its location. It's hacking the nervous system of other animals using electricity. These creatures represent the outer limits of biological possibility. They're not anomalies. They're the result of millions of years of evolutionary pressure, selecting for solutions to specific problems. And evolution, given enough time, produced these impossible solutions. What makes these creatures so fascinating isn't just that they possess these abilities, it's that we can't replicate them. We have electron microscopes, supercomputers, advanced materials science, and billion-dollar research budgets. And we still can't build a mechanical system that matches what the mantis shrimp does with organic compounds and calcium carbonate. We can't create a self-repairing composite material that operates at the stress levels of a mantis shrimp club. We can't design a spring-loaded mechanism that fires 50,000 times without wearing out. We can't build sensors that process information as fast as a mantis shrimp's visual system. Evolution has been running experiments for billions of years, testing trillions of variations, refining solutions across incomprehensible timescales. The mantis shrimp isn't a random accident. It's the result of 400 million years of iterative design, where every generation that survived was slightly better optimized than the one before. The mantis shrimp is proof that the universe is stranger and more creative than we give it credit for. That the natural world contains wonders that rival anything in science fiction. That life, when pushed to its limits, can achieve things that seem impossible. And all of it is happening right now in burrows and reefs around the world, as it has been for hundreds of millions of years. The mantis shrimp will keep hunting. The bombardier beetle will keep spraying. The pistol shrimp will keep snapping. They don't do it for us. They don't do it to inspire our technologies. They do it because that's what they are. And in being exactly what they are, they show us the true depths of what's possible when life has time to explore the boundaries of physical law. That's the real wonder of the mantis shrimp. Not just what it can do, but what it represents. A creature so finely tuned that it breaks our intuitions. A reminder that we are still students, still learning, still discovering just how strange and beautiful this world actually is.